Swayam Prabha. Digital India. Educated India.
Let us start our today's lecture on soil dynamics. In machine foundations, in the previous lecture, a quick recap what we had learned. There are three major categories of machines: reciprocating machine, impact type machine and rotating type machine. And what are their special characteristics, that also we have seen. Like reciprocating machines produces mostly periodic unbalanced force. Examples of reciprocating type of machines are compressor, reciprocating engine, etc. Their operating frequency ranges are generally less than 600 RPM, and for their analysis we consider the unbalanced force as equivalent to a sinusoidal, because it is a periodic unbalanced force. For impact type of machine, it produces impact load, as the name suggests. Example of such machine is forge hammer, and operating frequency is generally between 60 to 150 blows per minute. And the characteristics of impact load, that is dynamic loads attain peak in a very short time and then die out. In case of rotating type of machine, examples are high speed machines like turbo generators, rotary compressors, etc. and operating frequency ranges between about 3000 to 10,000 of RPM. And basic design criteria for machine foundations we have seen. First of all, that foundation must be safe against the static load. So, we need to check against that no shear or bearing capacity failure occurs, and also no excessive settlement. Then coming for the dynamic load, we need to do three checks, actually against three criteria we have to design for. First one is no resonance condition, that is operating frequency and natural frequency of the machine plus foundation system should not match, they should be far away from each other. Dynamic amplitude must not exceed the permissible limit, and the third criteria is mostly qualitative in nature, which says that the vibration, it must not be annoying to the person working in the close vicinity, or it should not be damaging to the adjacent structures. Various methods of analysis are there for machine foundation design. First one is MSD model, that is mass spring dashpot model. Second one is EHS theory, that is elastic half space theory based on linear theory of elasticity. And the third one is a semi-empirical method, which is known as Tschebotarioff's reduced natural frequency method. And typical types of machine foundations usually designed are block type, box or caisson type, and wall or frame type. Also, we have seen that what are the various degrees of freedom for machine foundations, that is possible direction of movements, like 3 linear and 3 rotational directions of movements or vibrations. We name them as this one as vertical vibration, this one as lateral vibration, and this one longitudinal vibration. These two are also called sliding mode of vibration or horizontal mode of vibration in x and y direction respectively. Then about the rotational vibration, we have this one is called pitching vibration, this is called rocking vibration, and this one is called yawing vibration. As per Indian Design Standard Code of IS 2974 Part 1, the three basic criteria has to be satisfied for the design of machine foundation: dimensional criteria, then vibration criteria, and then displacement criteria. In case of dimensional criteria, we have seen how to select first the area of the block foundation. it says that size of the block must be bigger than the base plate size on which the machine is placed, and a guideline is provided that minimum all around clearance of 150 millimeter has to be provided, and the foundation block should be placed deep enough on a good bearing strata. Then combined CG of the machine and the foundation block should be as far below as possible from the top of the foundation to avoid any kind of unbalanced force or rotational force coming on the foundation. And eccentricity of the load should not exceed 5% of the least horizontal dimension of the foundation, so that no tensile pressure generates at the base of the footing, that we know from the static analysis also. In case of second criteria, that is vibration criteria, it says that any machine foundation can be designed either as overtuned or undertuned. In case of undertuned, to satisfy the no resonance criteria, the operating frequency and the natural frequency of machine plus foundation system, their ratio has to be maintained far away from 1, because they should not be close to each other. So, in case of undertuned, it is proposed that this ratio should be less than equals to 0.5 for important structures, or we can go up to say 0.6, it should be less than equals to 0.6 for less important structure. And for the case of overtuned machine foundation, this ratio should be greater than equals to 2 for important machines and greater than equals to 1.5 for less important machines. In the third criteria, as per our IS code, it says displacement criteria. In that case, the permissible displacement amplitude, dynamic amplitude of displacement should be always less than 0.2 millimeter. And another check is that qualitative check, what we told earlier, it has to be checked using the Richards chart, so that the displacement is not creating any problem to the people who are staying in the surrounding vicinity or working in the surrounding vicinity. We have seen what is Richards chart, that is for vertical mode of vibration, how we can find out whether what type of disturbances it is causing, whether not noticeable to persons to severe to the persons, and we should not cross this boundary or limit for design of machine foundation for the design. Similarly, for horizontal mode of vibration also we have seen that type of qualitative chart which we need to satisfy. Then coming to the design methodologies, we had started with the third method, that is semi empirical method proposed by Tschebotarioff, that is Tschebotarioff's reduced natural frequency method of 1953, and this was the derivation with this equation. So, let us see what are the design steps we should follow when we are going to design any machine foundation using this Tschebotarioff's reduced natural frequency. First step is omega. Omega is operating frequency, is given to us. So, let us record it, operating frequency. Second step, assume the value of omega n. When you are assuming the value of omega n, automatically you are assuming f n, okay, either circular or full natural frequency. How you are assuming this value? Remember the design guideline of either overtuned or undertuned case, that it is using either this ratio of omega by omega n less than equals to 0.5 or greater than equals to 2. So, that is the second step to assume the value of omega n based on the no resonance criteria. The third step is size of the machine base plate, that is base area of the plate, we have to assume by considering minimum all around clearance of 150 mm, what is given as per the code. So, finally, we will get area A, because base plate size will be given to us by the machine provider. So, base plate size you know, you add all around clearance of 150 millimeter. So, you will get the minimum area required to be provided for your foundation block. Fourth step is assume depth of the block foundation, that you have to assume here. What is the typical assumption? Typical assumption is generally 150 millimeter or 15 centimeter. Start with that. That is the minimum depth of the foundation or footing has to be provided. Remember, in codal guidelines also, the depth of footing has to be provided, minimum thickness of the depth is 150 mm. So, that criteria you use here also. You can assume any value more than or equals to 150 mm. Then next fifth step is find out the total weight. Total weight means total weight of foundation and the machine. Machine weight will be given to you, and weight of the foundation you can easily now calculate, because depth you have assumed, area also you have assumed. So, volume you know, if it is a RCC block, use the unit weight of RCC, you will get the total weight of foundation, add it to the machine weight, you will get the total weight of the system. Next step is compute that Q naught, contact pressure, from this calculated value of W and assumed value of A, what you have selected. So, you will get the Q naught value. Seventh step is calculate that reduced natural frequency of Tschebotarioff using this equation. Fn already you know, because we have assumed using no resonance criteria. So, Fn you know, Q naught you have calculated just now in the previous step. So, using this you can get the FNR. Next step says, now you have to use Tschebotarioff's design chart. Tschebotarioff have given design chart of this FNR versus area of the foundation based on different soil properties. And ninth step will be, so what you have to do, you have calculated this FNR, go to Tschebotarioff's design chart, corresponding to FNR, find out what is the area required to be provided, and in the next step what you are checking, check whether area required is less than of area what you have provided or assumed in the previous step, then it is okay. Fine. We will see the Tschebotarioff's chart just in the next slide. Before that, let me mention one very major drawback or limitation of this Tschebotarioff's reduced natural frequency method is that displacement criteria is nowhere mentioned. Using this method for the design of machine foundation, you cannot check how much dynamic displacement amplitude your foundation is going to face. The only criteria we are checking here is the no resonance criteria, right. That is in the second step, while selecting your Fn value, you have used that no resonance criteria, but second and third criteria there is no chance that you can check for. So, that is the major drawback of Tschebotarioff's reduced natural frequency method. Let us now look at Tschebotarioff's design chart. So, this chart, the first one, what it shows, FNR in the x axis, which is nothing but reduced natural frequency, and y axis is A, that is area in the unit of feet square. As I have said already, these are semi empirical methods. So, units you have to be very careful, all are in FPS unit. Area, when you are providing or you are getting or using from this chart, what you will get in feet square, then you have to convert it in your SI unit, what you are using. And unit of FNR, FNR is also having a particular unit. What is that unit? That is CPM, that is cycles per minute root over tons divided by feet, right. Let us go back to the equation, you will easily understand why the equation or why the unit of FNR is so. What is the unit of Fn? CPM. So, unit of root over Q naught. What is root over Q naught? Ton per feet square under root. So, obviously, root of ton by feet, right. Now, for different soil, Tschebotario has given this chart. For sandstone this line, for sands this line, for plastic clay this line, for peats this line. So, depending on your nature of soil, you can select which line has to be used. And also, if you check carefully, if you try to derive the expression, you can also derive. These charts are not abruptly developed, these are based on G values of the soil. So, the slope of this line, the theta, you can calculate easily based on the G value of the soil. That is what Tschebotario has done. If you try to further simplify the expression of FNR, you will get that in terms of the G value of the soil by representing the K dash, that is dynamic subgrade modulus. Second, Tschebotario's design chart is like this. X axis is same, that is FNR in the unit of CPM root over ton per feet square, whereas y axis will give you the value of 1 by 4th root of A, where A is used in feet square unit. So, if you use this chart, second chart, for different types of soil, again he has proposed here for sandstone, sand, plastic clay, peat, you can get different angles, that is what it is mentioned here. The slope of the line, which will be easily help you to get for different calculated value of your FNR in the design steps, whatever I said, to this 1 by 4th root of A value very easily, and that is your A required, okay. And A provided, you have to check with this A required till they match, or if your provided area is more, then it is fine. Now, both are Tschebotario's design chart. As a designer, which chart you will prefer to use? Both are same chart. What are the basic differences between them? If you look very carefully, this first chart is having this and this axis both in log scale, whereas the second chart both x and y axis are in natural scale. So, if you read your design value from this chart, to reduce the manual error, it is always better to use the graph with natural scale than logarithmic scale, because in log scale, if you miss a very small point, small distance, it will be magnified hugely. So, that is why among these two charts, same charts, the second one is preferred for design purpose, though it will give you a complicated value of expression of y axis, from which you have to recalculate the area, whereas in the previous chart it was pretty direct, you were getting the direct area, but still the second chart will be preferred in the design. Okay? We will do some example problem also, how to design a machine foundation using Tschebotarioff's reduced natural frequency method. So, in the next lecture we will do that. We are continuing with our module 5, that is machine foundations. So, today we will design some machine foundation using this Tschebotarioff's reduced natural frequency. Let us first see the problem statement. What it says, that design a block type machine foundation for a machine of weight of 0.5 ton with minimum area of base plate as 45 centimeter by 60 centimeter. That is the area of the base plate and this is the weight of the machine. So, these two input parameters will be provided to us by the machine manufacturer. So, for this machine, to house this machine, we have to design a block type of foundation. Also, the machine manufacturer will be given us the operating frequency of the machine. So, it is given that operating frequency of that machine is 1500 RPM. Now, using Tschebotarioff's reduced natural frequency method, we need to find out the size of the block foundation for three different types of soil. That is, suppose if we have three different types of soil, what are the different sizes of foundation required to be provided to place this machine which is given to us. So, this is clearly a complete design problem which we need to consider, and the G value for these three different types of soil are given as the first one as 50 kg per centimeter square, second one 100 kg per centimeter square and the third one is 200 kg per centimeter square. And it is mentioned that assume the Poisson's ratio for all these three types of soil as 0.25. Remember, this kg per centimeter square unit is nothing but equivalent to or equal to TSF, that is ton per square feet. Why it is given? Because while using Tschebotarioff's design chart, we need to convert all the values to FPS unit, because his basic design chart is given in FPS unit. So, with this given problem, let us start designing the machine foundation. Let me tell you first, I am not covering the static part of design here. So, remember this one. When you are doing a design, in actual case, first you must check under static load whether your chosen foundation is safe or not. That is, bearing capacity failure and excessive settlement failure has to be checked. Now, beyond that, only for the dynamic component I am showing you the design procedure here. So, that does not mean that it is the only component for the design. So, remember this one. I am only covering here under dynamic load whatever the design criteria. So, let us see step wise. In step 1, the given value of operating frequency is 1500 RPM. It is given to us. So, the step 2 says assume Fn, that is natural frequency of the machine plus foundation system. So, in that case, so for under tuned, what we are getting Fn is F by 0.5, that is 1500 by 0.5 will give us 3000 RPM for over tuned. We are getting Fn equals to F by 1.5 1000 RPM. Okay. Now, let us move to step 3 of the design. in step 3, what was mentioned, that based on the given base plate size, what is the base plate size? Let us look at the problem statement. Base plate size is given as 45 centimeter by 60 centimeter. And what we know from IS code design specification, that minimum all around clearance of 15 centimeter needs to be provided. So, this is 15 centimeter and this is also 15 centimeter, whereas this dimension is 45 centimeter and this dimension is 60 centimeter. Okay? This is the minimum area required, remember. We of course can provide bigger area also. So, the minimum area of block foundation will be 45 plus 2 times 15 multiplied by 60 plus 2 times 15. So much of centimeter square. It comes out to be 6750 centimeter square. We need to convert this to FPS unit for using Tschebotarioff's design chart. So, let us convert from centimeter square to feet square. So, if we use conversion factor, it will give us 7.266 feet square. Okay? So, this is step 3. Now, let us move to next step, step 4. Step 4, it says assume height of foundation. So, let us assume height is minimum thickness of the foundation, what the guideline says 15 centimeter. Thickness of the footing or thickness of the foundation 150 mm. Let us convert it to FPS unit of feet 0.4921 feet. So, next is step 5. What it says? Find out the total weight of machine plus foundation system. So, weight of foundation WF, that will be area A times height H times unit weight of, let us say it is of concrete. So, concrete. So, if we put the standard value of unit weight of concrete and this value of A and H in FPS unit, 7.266 feet square is the area, height is 0.4921 and unit weight of concrete is about 0.0708 ton per feet cube unit. So, this will give me unit of tons. This is the unit weight of concrete 0.0708 in the unit of tons per feet cube. So, it is giving us about 0.2532 tons as the weight of the foundation. So, in this step 5 only, we have to now compute the total weight of machine plus foundation. Weight of the machine is given to us, which is 0.5 ton, right. Total weight of machine plus foundation system that is W equals to 0.2532 plus 0.5, so much of tons. Fine. So, it is giving me about 0.7532 of tons. Now, in the next step, step 6, what it says? Compute the uniform bearing pressure below the footing, that is Q naught as per the nomenclature of Tschebotarioff's reduced natural frequency method, that is W by A in ton per feet square unit. So, 7532 by 7.266 ton per feet square. If we calculate this, we will get 0.1037 tons per feet square. This is Q naught. Let us move to next step, that is step 7. It says, let us calculate FNR, which is Fn times root of Q naught. So, this is the formula given by Tschebotarioff's reduced natural frequency method, which we are using here. Now, we have two cases here for under-tuned FNR is coming out to be, Fn is how much we got? 3000 RPM, right, times Q naught we got 1037. So, RPM is nothing but same as CPM, cycles per minute or revolutions per minute, it is nothing but the same unit. That is what the chart of Tschebotarioff's method use the unit. So, we can write down in same form CPM root over tons per feet square, that is the unit. It is always better to write the unit side by side, so that we are following the whatever is given in Tschebotarioff's chart. It is not dimensionless. So, that is why we have to be careful while using this semi empirical method. So, let us calculate this, how much it is coming? It is coming about 966.1. So much CPM root of tons per feet square. Okay? Whereas, if we go for the overtuned design, in that case FNR is, Fn is how much? 1000.1037 So, how much it is giving us? About 322 CPM root over tons per feet square. Okay? So, this is step 7. In the next step, step 8, what we need to do? We need to use Tschebotarioff's design chart, which I had shown earlier. So, step 8, use Tschebotarioff's design chart that gives for various G values, that is against the calculated FNR in the previous step. Using various types of soil based on various G values, we can get the area required. Now, if you look at the equation is given for the Tschebotarioff's design chart in normal scale, the second graph or second design chart, whatever I have given earlier. The form of equation is FNR times tan theta equals to 1 by 4th root of A. That is the equation. This is the equation of a straight line. Let us look at the chart here once again. So, in this chart, this is y axis, this is x axis. So, equation for all different types of soil, equation is nothing but a straight line equation passing through origin. So, it will be y equals to m x equation. That is why I have written it in the form of here y equals to m x. And what I had mentioned to you earlier, if you try to derive from the basic of the formulation of Tschebotarioff's reduced natural frequency method, you will get the expression for tan theta in terms of G will be like this: pi to the power 5 by 2 1 minus mu 10 to the power 4 divided by 36 small g times capital G. Small g is acceleration due to gravity, capital G is shear modulus of the soil, mu is Poisson's ratio of the soil. So, this expression can be easily obtained or derived from the basic of Tschebotarioff's method, what I had explained earlier. So, you can try to derive this one. So, what we will do, instead of using his design chart, that is one option of course. That is how he has developed that design chart actually, based on different mu and G value of the soil. These two are soil properties. Now, instead of using the design chart, as we know this expression, we will directly use this value for computation of this tan theta, which will give us this value of A finally. So, now for the given problem, we have mu equals to 0.25 for all the types of soil, acceleration due to gravity G in terms of FPS unit is 32.4 feet per second square, and we have 3 cases of capital G, that is shear modulus, as 50 ton per square feet, 100 ton per square feet and 200 ton per square feet. These are the 3 G values of the soil given to us, that is in 3 different soil conditions we have to design the foundation. Okay. So, let us now calculate this tan theta using this expression. Tan theta for the first case comes out to be 1.5 approximately for G equals to 50 TSF. Please put the values of known parameters in the equation and check if it is so. The second type of soil, tan theta is coming out to be about 1.0606 for G equals to 100 TSF. Please check if you are getting this value of tan theta for G equals to 100 TSF. And in the third type of soil, tan theta is coming out to be about 0.75 for G equals to 200 TSF. So, after this we have to go to next step, that is step 8, where we had already calculated this tan theta values using Tschebotarioff's chart in the same step actually. Now, corresponding to this FNR value and tan theta we have calculated, we can calculate the A value in the same step. So, for the first case, what we are getting, 1 by 4th root of A is equals to 1.5 times FNR, first type of soil, which will be how much? 1.5 times FNR is 966.1. So, it will give me a value of 1449.15. This is for the case of undertuned, right. And the other case for overtuned, it will be 1.5 times FNR. In that case, FNR how much we got? 322,483. This is for overtuned. Okay? Do not write the units here, because here the unit will be 1 by 4th root of feet square. So, from this what we will get? A required, because the Tschebotarioff's chart or Tschebotarioff's equation will give us A required. If we use this, how much we are getting? 2.27 into 10 to the power minus 13 feet square for undertuned. Okay. Whereas, for overtuned case, we are getting 1.84 into 10 to the power minus 11 feet square for overtuned. Both of them are much less than A minimum, whatever is required based on the dimensional criteria. Okay. So, why this such a low value comes? We will see soon. It is because of, it seems that already the base plate of the machine, whatever it is provided, is very, very good enough to take care of the vibration. So, that is why, truly speaking, no more size or extra size is required. So, minimum size provided based on the dimensional criteria to keep the free clearance all around, we are getting the much more than what is required from this analysis. but we will see we have to check this once again in terms of another parameter. We will come to that soon. So, this is for first type of soil. Let us do this for other two types of soil. For second type of soil, where G is 100 TSF, in that case, how much we are getting? 1 by 4th root of A is tan theta, that is 1.0606 times FNR, which will give us 1.0606. FNR is 966.1, is 1024.65. That is for under tuned. For the other case of over tuned, it will be 1.0606 times FNR is 322, 341.5 for over tuned. So, finally, how much they are coming? A required of under tuned will be, for the first case of under tuned will be 9.1 into 10 to the power minus 13 feet square. For case of under tuned, and 7.35 into 10 to the power minus 11 feet square for the case of over tuned. Again, both of them are much less than A minimum. Fine. Now, for the third type of soil, that is for with G equals to 200 TSF, what we got? This equals to tan theta, we got as 0.75, right, times FNR. $724.6 for the case of under tuned, $241.5 for case of over tuned. So, which is giving us A required as 3.63 into 10 to the power minus 12 feet square for under tuned, and 3 into 10 to the power minus 10 feet square for over tuned. Again, both calculated values are much less than A minimum based on the base plate dimension. So, what does it mean from these calculations using Tschebotarioff's method? That whatever size we had provided for the block foundation, so we had provided 15 centimeter thickness, this dimension we had given as 75 centimeter, and this dimension we had given as 90 centimeter. Whereas, on top of it the placing of machine base plate should be done like this, So that this clearance of 15 centimeter all around is available. That is the design component. Now, this is provided size is much more good enough than whatever we are getting from Tschebotarioff's chart. Does it end the design process here? No. Why? Here, why it is not ending the design procedure? Because we are not yet sure whether no resonance criteria has been satisfied or not. The provided size, based on provided size, we have not calculated the value of natural frequency of the entire system. Unless that is far away from the operating frequency, we cannot say that this provided dimension is safe. So, it is not the end of the design, but some more checks have to be done. So, it is a repetitive process unless both the things are satisfied. Let us do that. So, with this dimension what we have provided, now let us go back and calculate the area. Area is 75 by 90 centimeter square, which is giving us 7.2656 feet square, from which what we can do? We can find out the equivalent radius of a circular footing. This is of course our rectangular footing we have provided. That, suppose if we want to find out equivalent radius of a circular footing keeping the area constant, therefore, R naught will come as how much? A by pi 1.521 feet square. Sorry, R naught is 1.521 feet. That is called radius of equivalent footing base. Why it is required? For vertical vibration, the stiffness of the system K is computed by this expression 4 G R naught by 1 minus mu. This expression based on the theory of elasticity was developed by Timoshenko and Goodyear. So, in the book of Timoshenko and Goodyear you will find this expression for vertical mode of vibration. The stiffness of the system is calculated in terms of the size of the foundation and the soil properties. So, 4 G is shear modulus of the soil, R naught is this equivalent radius of the circular foundation, mu is Poisson's ratio of the soil. So, with this knowledge of K, which is required of course to calculate the natural frequency, because natural frequency we need root over K by m. M of course, we can calculate from the size provided. We know the m, what is the mass of the footing, but K we need to compute. So, with this we will stop our lecture today here. We will continue further in the next class.